Hello everybody, this is Carol speaking. Welcome to this PolyWorks webinar. And just a heads up, this is the last webinar of our series. So let's get to it. Today we're talking about how to align symmetrical parts by balancing deviations. Let's welcome Jean-Sébastien Blais as he is our presenter today. Jean-Sébastien is a member of the technical support group. Let me remind you that if you have any questions during the webinar, please use the questions panel. I will be monitoring the questions throughout the webinar. We will have a short Q&A session at the end. If we don't have time to answer all of the questions, we will get back to you by email. And yes, we are recording this webinar, so it will be available for later viewing. Jean-Sébastien, it's all yours.
Thank you, Carol. If you are inspecting parts with symmetrical features, you're probably trying to align them so that you get equal deviations on opposing sides of a symmetry axis. Reaching that goal is difficult with traditional alignment tools since the symmetry axis is in fact an imaginary line that must be constructed. In this webinar, I will demonstrate how you can build a reference target alignment that uses dependent features constructed from different measurement objects to establish that symmetry line. Let's take a look at this part that is the interior of a car hood. Now, as you can see, I've already imported the CAD model, and I've performed some surface scans along with some boundary scans from the periphery of that part. Now, you may have also noticed that I've already performed a best fit alignment that actually brought the surface data on top of the CAD model. Now, let's start by looking at our final alignment requirements. So first, we would like to use 4 points in the Z direction that are actually symmetrical on the part to actually lock the up and down direction on that hood. Then we're going to use a set of additional 4 points that will lock the lateral translation, and these are the points we would like to have symmetrical deviations on. In addition to these, we'll also lock the final translation along the x-axis or along the axis of the car to perform the reference target alignment. Now let's build that reference target alignment in PolyWorks Inspector. So for that, I will start by creating some surface reference targets from the point we saw in Z and Y direction. And since I already have those coordinates typed in a text file, I'm going to create those points from that file. Now notice that in addition to the coordinates, I also have the name of those points. So I will read the file with a template that includes the name. Now note that the alignment direction is automatically set as I am importing those points, and it's actually finding the closest axis that match the CAD surface normal the point lies on as the alignment direction. So this is all good for our Y and Z points, and for the 2 points that are bound to the holes, I already have the holes being created. So I'm going to go ahead and create some surface reference some feature reference targets from those holes. So I'm just going to go ahead and name this one X1, and I'll make sure they are created from those existing objects and locking the X direction. Now you'll notice that these points already have a deviation simply because the measured components of those features are already extracted in the project. Now that we have all our reference targets, we are ready to perform the reference target alignment. Now the first thing you will notice upon completing this alignment is that none of the points are in tolerance, but let's focus our attention on the points that are locking the Y direction. What's obvious here is that our deviations aren't balanced. By balance, we mean having equal and opposite deviation on each pair of mirrored points. Now, the reason why the reference target alignment did not produce the expected result is simply because the reference target alignment is designed to minimize the deviation on all the points. Now the reason why it's not exactly giving what we want is probably because by trying to make the deviation balanced here, it probably led to increasing the deviation on some of the points that are currently not shown. Thus, it led us to that result that minimizes all the deviation. Which brings me to the following question. How can I make sure I will balance the deviation on each side of the symmetry axis? By building reference targets that are bound to that symmetry line. Let's go back to our drawings to better understand this. So this is the actual imaginary symmetry line I'd like to establish. Now, rather than using those two opposite points on each side, I can use any measurement object I can think of to actually derive a midpoint that would stand exactly where that symmetry line is. So that is the reference targets I would like to use in my alignment. Now, if I do the same for y2 and y4, then I can transform the 4 original y points into 2 midpoints that I will use as my reference targets. Let's take a look at how we can do this in the software. Now, the easiest measurement object to use to actually obtain a midpoint from pair of symmetrical points like this would probably be the caliper gauge. Now, rather than creating calipers by typing in the values or by anchoring them randomly on each side, I'm going to choose to create those calipers numerically. And here's one trick I really like. Whenever you have a point that you would like to use in defining a caliper, you can always drag and drop it onto the text box where you see the coordinates of the points you'd like to obtain. So in this case, if I hit create, you're going to see the first caliper being created from y1 and y3. Now from that caliper, I can create a midpoint that would be dependent. So in this case, I will create from a caliper and I will create the midpoint. Now the key item here is to make sure create dependencies is on, and it is generally by default. So this is the midpoint that I'm going to be using. Now if you want to see where that midpoint is, let me just hide the caliper, and this is the point we just created, which is exactly in the middle of y1 and y3. So this is also the point I'm going to be using to create a y13 reference target that will be created from that point, and that will be locking the y direction. Now I'm going to repeat those steps simply for the other pair of y2, y4 reference targets. So in this case, I will create a caliper, from y2 and y4. So this is our caliper. This is the midpoint that goes along with it. And from that midpoint, I will simply create the reference target that I need called y2 and y4. Now this also means I no longer need those reference targets, but before I get rid of them, let me just get rid of the alignment to avoid having update errors. Now, let me go back to my drawing because there's one more thing I would like to do in here. So we talked about the fact that we wanted to use two holes to perform the alignment along the x-axis. Now, since the symmetry is already handled by the y points, these two holes will not set any symmetry with respect to the black axis here. However, I can balance the alignment with respect to any axis. For example, the axis that you see in red here that links the two center point of these holes could be used to perform balancing. What I mean by that is if this is the actual hole on one side and the hole on the other side, if I only use one of the holes here, hole x1 will have 0 deviation, and I will have a very large deviation magnitude on the opposite side hole in terms of x coordinate. Now, if I do the opposite, then you understand that this deviation will be on the X1 hole. So what I would like to do in terms of balancing in this case is I would like to distribute that deviation so it's half on one hole and the other half on the other hole. Again here, I will get equal and opposite deviation, but we're not talking about symmetry here. We're just talking about balancing on each side of an axis. Now in this case, in order to do that, I can use those features which are measurement objects to derive a dependent midpoint that will be our X1, 2 point and use that rather than using the reference targets that were bound to each hole. Again, let's do that in the software. So these are the two holes that we would like to use. Let me start by creating a dependent point feature from those holes. So that will be point X1 from the circle center. And then I will do the same for the slot. So now I have 2 point features that can be used to create a single midpoint. So this one will be called midpoint X1, X2, and it's going to be created from the average. Again, this one's slightly underneath, so we don't see it here. It's here. And I will use this to create my reference target that will be called X1 and 2, and this one will be locking the X direction. And now with all these, I no longer need those X points, and I can actually perform the reference target alignment and hope to see something that will be balanced. So we start our alignment. And if everything works as planned, we should get balanced deviation in the Y direction and balanced deviation when we look at the X coordinates of these holes. So almost done here. So first thing you will notice is that, yes, all the reference target points are inside the 0.1 millimeter tolerance, but that's not our main focus here. Here, what I would like to take a look at is make sure that my deviations are balanced. Unfortunately, when you're using calipers to see if deviations are balanced, you're actually short on having a deviation at each end. Now, it's not mandatory to do what I'm about to do, but let me just show you. If you want to verify that the deviations are in fact balanced, you can always create some point features from the ends of each caliper. So I'm going to create the endpoints of the calipers and see my deviations. So in this case, it's just a matter of showing the Y control on those. And as you can see, I have equal and opposite deviations on these mirrored points. And we do have the same thing on our X1 hole and X2 hole. As you can see, we have equal and opposite deviation there as well. This is possible because since the release of PolyWorks 2018, the reference target alignment recalculates dependent primitive within its iterations. So you just saw that we could use Caliper to derive a dependent point to which we could bind a reference target. We did the same thing using features. So we used 2 holes to actually derive a dependent point. Actually, this is a flexibility that PolyWorks has where you can use any measurement object to create those dependent primitives that will allow you to derive the symmetry axis, whatever point feature you need to perform the alignment as you wanted. So let's just push things a little further by showing you another measurement object that can be used to balance an alignment. So if we take a look at our alignment, you can see that the Z points, so I'm going to get rid of these, the Z points are currently over constrained. We have 4 of them, which means that they cannot zero out completely. Let me hide those holes and we'll take a look at the front end of the car. For example, these holes, Z1 and Z3, are actually very close to the hinge holes. Let's say for some reason we cannot tolerate any deviation on those points. Otherwise, we'd have to put shims, and we want to avoid that. So in this case, we would like those 2 points to zero out. If we do this, it means that our front end points, Z2 and Z4, will actually increase in deviation. But what I would like to make sure is that by transferring the deviation to those points, I would like to make sure they are still balanced. So in order to do that, I will apply a very similar strategy by combining Z2 and Z4 into a single dependent point. Now, those are not holes. They're actually just points that lies on the surface. So what I'm going to do is I'm going to use surface comparison points in order to replace those two reference targets, and I will derive a midpoint from these. So before I do that, let me just return to the original alignment, the best fit. I'll get rid of the reference target alignment we already have, and again I will create from Z2 and Z4 2 surface reference targets that I would like to use. So this one will be created from those selected reference targets. And right now, I can get rid of Z2 and Z4. Let me just get rid of the color map. And what we would like to do is derive 2 dependent points from those comparison points, from which we can actually derive a midpoint, Z2, Z4. And this happens to be the point I want to use. Sorry, made a typo here. This is the point I would like to use as a reference target. So this one will be called Z2 and Z4. And this one will lock the Z direction. Again, we're back at square one, where we would like to balance our alignment. So these are the reference targets I plan on using, and this is what I'm going to get by using that set of reference targets that I could have created from the start if I didn't have to demonstrate all those steps one at a time. So once the alignment is completed, you can see that I have equal and opposite deviation at the front end, whereas the points that are nearby the hinge holes now zero out. And in addition to that, if I go back to my caliper endpoints, you can see that I still have equal and opposite deviations that are symmetrically distributed on each side of the part. And same thing for our hole features that currently are perfectly balanced. So to summarize, what you should remember from this webinar is that having the capability to derive reference target points from a variety of measurement objects gives you additional flexibility and power to create the exact alignment you need.
Thank you, John Sebastian, for this webinar. And just a reminder, this webinar has been recorded. It will be available on the Innovametrics software website. Navigate to the support section. It will also be available on the Innovametrics software channel on YouTube. And as I said earlier, this is our last webinar of the series. We're going on the summer break, but we'll be back definitely in September. Please check the website for all the details on exact date and topic that we will be getting to in September. In the meantime, I do invite you to browse the support section of our website. We have quite a collection of webinars and definitely interesting tools in there. Thank you for joining us this morning, and we'll see you next time. Bye-bye, everybody.